So good morning. Thank you all for coming this session today. So my name is Yeseul Jeon, and most of you may not know me yet because I recently started my postdoc at TAMU, this department under Professor Raj. And even though I delivered this presentation with this topic more than two times, it's still nervous for me to speak not my native language, but if you have any question regarding my research, please interrupt me at any time and I can respond it more than I can do. And yeah, if I cannot follow right now, then I can follow up through the email. So today I'm going to talk about the Bayesian convolutional network space generalized linear model. So this is not a rocket science thing. It's just a really simple idea, but back then no one had considered yet. So yeah, so I would like to start with the introducing my research problems, and then I would like to introduce our model. And due to the time constraint, I only brought two application cases which validate our models. And I would like to end up my presentation by summarizing our idea. So in the real world, you can encounter many different types of data sets. For example, there are two different types. The first one is high-dimensional correlated structured data sets, which generally comes from in the forms of like matrix or tensor data sets, something like that. On the other hand, you can see a more familiar one, which is say standard vector type variables. So in the real world, we can encounter these two different types of data set frequently. So, and let's assume that you're a doctor and you have a patient with a tumor. Then you're gonna take a brain scan to that patient to check whether that patient has a tumor or not. So you take that patient to have brain MRI scan so that you can obtain the MRI image data set like that one. And also to make a really well decision whether that patient has a tumor or not, you also want to consider the demographic information such as blood type pressure or blood pressure or weight or age or gender or surgical history, something like that. So to make the decision that whether that patient has a brain tumor or not, you want to combine those two different types of data sets all together, right? So that you can make a right decision. And also you may want to know that what demographic information have a relationship with the incidence of brain tumor. So you want to understand the relationship, I mean, the association between them. Then how are we gonna model using these different types of data sets? So since you're the statisticians, we may come up with the idea of like, okay, why not we are using the generalized linear model. So generalized linear model, as you all know, this is the well-known model for estimating the coefficient of covariates. And also there are a lot of other regression model to handle the dependency data sets, for example, like spatial temporal models, which are also in the form of generalized linear model, or also you can use a random effect models, which consider the data dependency into the model as well. However, there's a limitations in this model because you cannot directly apply two different dimension of the data set into a one model, right? You cannot put the image data set into a generalized linear model. And also, when you want to handle the correlated structure data set, you have to create a covariance structure. And by choosing what kind of covariance structure you're going to use, it really affects the your computation cost to handle those covariance structures. Then you can also come up with the idea of, okay, then let's use the deep learning models. So deep learning model is really popular these days, right? And there's one typical model called convolutional neural networks. So in CNN, it has a convolution layer which trains the important neighborhood features from the input by shifting the corners over all pixel location so that they can understand the dependency structure within the data set. But still, it has a limitation in using these CNN models into that research questions, because in general, it is the deep learning model cannot fully quantify the uncertainty in estimation or prediction. And also, it is hard to interpret the covariate. I mean, it's hard to calculate the coefficient of covariates in the form of the DNN structure or deep learning models. And this is because most of the deep learning model, it relies on the stochastic gradient descent algorithm, which only based on the prediction accuracy, not on the convergence in parameter estimation. That's why it's hard to define that we can interpret the parameters of the covariates. So our research goal comes to solve those problems. So first one, okay, let's handle these different types of data sets simultaneously into our model, which is really frequently we can saw in various applications. And second, let's estimate the coefficient of covariates, because we want to know how those variables are related to the responses. And third, we also want to quantify the uncertainty in estimation and prediction as well, so that we want to construct the posterior distribution of coefficient, and we also want to derive the predictive distribution so that we can quantify the uncertainty in prediction as well. So those three are the points that you have to remember after my presentation. So how our model handle the two different types of data sets, image with the vector type covariates, and the second, how we estimate the coefficient of that covariate, and third, how our model quantify the uncertainties. So before introducing our model, I would like to start to introduce the notation that I use in this slide. So let's say there's a D, which is the data set, and Xn is the input, Yn is the output response. And in our model, we use the deep learning model. So there is a large L number of layers, and each L layer has a KL number of nodes. Yeah. Yeah. And in deep learning model, there are parameter sets, WL and BL. So here, the WL indicate weight matrix, where which connects the previous nodes to the previous L-1 node to L layer. And there's a bias vector type parameter. So equation 1 is a simple neural network structure with the dropout. So when you model the high dimensional data set, DNN requires not only the DNN, but neural network requires a more complex structure of the neural network structure. So it requires a large number of layers and large number of nodes, which cause the overfitting problems. So to solve these problems, dropout has been suggested. So here I write the dropout as a DL. So dropout is simply just when you train the model, it randomly select the weight parameters or the bias parameters to figure out what's the best for the model. And also you can regard this data generating function as F over here. So I'm going to use the mouse here. Yeah, here. You can regard this data generating thing as a F function. So yeah, each layer you can think about every layer has a data generating function in each layer. And once you plug to that ELF activation function over here, then I call it as a phi, which is the non-linear alpha feature from the Lth layer. You can just regard this phi as a node values. Yes. So the idea of this model, we based on the deep Gaussian process. So one can regard this data generating function f as a deep Gaussian process because the input is also follows the Gaussian process, and output also follows the Gaussian process. This is called a deep Gaussian process. So as the structure of the neural network has a similar pattern with the deep Gaussian process, because when you put the L-1 follows the Gaussian process, then that value is also the input for the Lth layers Lth layers input data set. So I mean the L-1's output is also the Lth layers input data set. That is we can regard that neural network structure as a deep Gaussian process. So here the point is we can construct the Gaussian process where the covariance structure is empirical covariance structure matrix over here. So you can see the N-1 output feature phi is combined with Lth number of weight and bias parameter, Lth bias parameter. Yeah. Okay. So then the next question is, since we want to know this parameter distribution, right? So one may choose the Monte Carlo, Markov chain Monte Carlo things to approximate the posterior distribution of the weight parameters. However, it costs a lot of computation, right? So we try to approximate the weight and bias parameter using the variational base, so that what we have to do is construct the variational distribution. So we can construct the variation distribution as follow in equation 4. So you can see there is a Q variational distribution for weight parameters. So with the some amount of the PL, which is a probability between 0 to 1. So let's say PL goes to 0, then the QWL follows to normal distribution where mean is 0 and the variance is sigma square. And it shows that the WLIJ is probably to have a value of the 0, which is the same effect of applying the dropout to that else weight, which is WLIJ. So you can also construct the variational distribution for bias parameter as a mixture normal distribution as well. And then all you have to do is estimate the variational parameters of the weight and bias. So it's a typical thing that we can use the elbow to estimate the to estimate the variational parameters for variational distribution of weight and bias. However, as you can see in the equation 5, it's really hard to directly maximize the equation 5 due to the intractable integration. So the Gauss replaced it with the Monte Carlo approximation as shown in equation 6. So here the WL upper M and BL upper M indicates the MC samples from the variational distribution that I have shown in previous slides. So this is all about the MC dropout, because the MC dropout is a simple thing. So like it uses a variational base for the Gaussian process model to estimate the variational distribution for the weight and bias parameter. And it approximates those parameters using the Monte Carlo approximation. And the point is that Gauss showed that applying the dropout DL after every hidden layer L can approximate the objective function of VB for deep GP. It means that you just frequently, in the frequentist perspective, you apply the dropout to the neural network. It shows the same effect. You're approximating the deep Gaussian process using the MC dropout. Okay, so that is the MC dropout. And the reason why I introduced MC dropout is we adopt this technique to approximate our models. So I will catch up that stuff in later slide. So then, since my research goal of the first one is how our model going to simultaneously combine two different types of data set into my model. So our idea was to, okay, let's train the input image X with the response Y, because deep learning model is well known for handling the correlated structure data. Then we can extract the last layer nodes from the trained deep learning model, which is feature phi over here. I call that as a feature phi. And this feature phi summarizes the high dimensional input X to a lower dimensional space vector type data sets, right? Because we extract the values from the last nodes, which is in the end just a vector type. So we can regard this phi as a basis design matrix that encapsulate information of X. And this can be regarded as a summary statistic, which is useful for predicting the response variables. So that one was our idea to extract the information from the input X and make that to match the dimension of the covariate, to make them as a vector type. So this is our model-based CGLM. So since we obtained the features phi from the neural network, and also we have a covariate of Z over here, and our second goal is to estimate the coefficient of the covariate, right? Then we can use the generalized linear model, which is well known for handling the coefficient of covariate. So we just simply combine the phi and Z into a GLM model, and now we can interpret the association between covariate Z and response Y through the gamma parameter over here. Then the next question, then the last one is how our model gonna quantify the uncertainty in estimation and prediction. So to do that, we first construct the posterior distribution of coefficient. So equation 8 is a posterior distribution of beta function over here. And here the pi beta given D is the observed data set, and WL, BL are the parameter set from the neural network. And it's the conditional posterior distribution. And here the pi WL given D, pi BL given D are marginal posteriors for weight and bias respectively. And since it's really challenging to compute the equation 8 directly, right? So we approximate through the MC dropout that I introduced in the previous slide. It's the same technique. So we approximate our pi WL given D, pi BL given D using the variational distribution of the weight and bias parameters over here, the Q, WL, Q, BL, and then we use the Monte Carlo approximation to equation 9 so that we can obtain the Monte Carlo samples so that we can approximate the beta posterior distribution. Then you see the next question is, what is the pi beta M given D? We have to define that distribution as well so that we can aggregate the Monte Carlo samples from those distribution, right? Then one can use the Monte Carlo, Markov MCMC things to approximate the pi beta M given D and WL, BL thing, but it is really time consuming to get the good mixing of the samples. So our idea comes to use the Laplace approximation to that. So here's the thing. So first of all, you compute the phi m from the given WLM, BLM through the forward propagation. And here the WL and BL are the MC samples from the variational distribution. And then second, you obtain the maximum likelihood estimates beta hat m using GLM by regressing y on phi m and z. And then you can approximate the posterior distribution of beta m to follow the normal distribution where the covariance structure is B hat inverse m. So here the BM hat is the observed Fisher information matrix from the nth MC samples. So equation 11 is the finalize our approximated posterior distribution of beta. So here the psi indicates the multivariate normal density with the mean and the covariance structure. So that's the way how we estimate the uncertainty in estimation in coefficient of covariate. And then the next question is then how are we gonna quantify the uncertainty in prediction as well. So we derive the predicted distribution based on the equation 11 that I showed before. It's about the posterior distribution of beta. So here the AM star indicates the test data sets. So we can calculate the phi star m using the X star and the G star, which is test data sets. And then the predictive distribution of the linear predictor goes like equation 12. So based on your response type, you can generate the predictive distribution based on different distribution. For example, when you assume that your response data set follows the Gaussian responses, then you can derive the predictive distribution Y star through the normal distribution, where the mean and the sigma square is written as in this slide. You can also calculate the count response data set and also binary response data set. So actually, there are a lot of things too in mathematical thing, but I will spare the details for you because you can also see that details in my supplementary materials. However, what I want to point out the thing is why we then use a two-stage approach rather than using a just one-stage approach. For example, so as I introduced the Monte Carlo dropout, the MC dropout in the previous slide, the Gao invented the Bayes CNN, which also can quantify the predictive distribution using the Monte MC dropout. That's a one-stage approach, right? You can simply just combine the covariate into the last layer, and then you can also put the image data set as input. And then that thing is you can model the two different types of data sets simultaneously. But why two-stage approach like ours? Because there's a limitation of using the Bayes CNN, because when you update the weight parameters, it shows a poor convergence in parameter estimation, especially with the high-dimensional data sets. One can just regard the corresponding weight parameters of covariate as a coefficient in Bayes CNN. However, it's kind of like biased because when you train the deep learning model, it has to simultaneously update the weight parameters to make a best model which shows the good performance in prediction, not on the parameter estimation itself. So then our model is the two-stage, but we make that complex optimization problem into a simple non-parametric regression problem by fixing the basis function of the input data set as a phi. So I got the comment when I doing my revision of things, then one of the reviewer asked me, but still, you're using the Bayes CNN or Monte Carlo MC dropout thing or deep learning model to get that phi, right? Which is true. We obtain the fee through the Bayesian deep learning model, and that Bayesian deep learning model train the weight parameters to obtain the highest prediction things. But here, the fee is still informative, even though they're from the black box model, is still informative when predicting the responses because it is obtained by minimizing the loss function, and we just want to get what is the best information from the input X to predict the response Y. And our model is more focused on the estimating the coefficient of covariate, not the fee itself. So that's the response that we did to the editor, reviewer. And yeah, I want to make sure that fee is still informative. And then this figure, we did some simulation study. So let's say the color indicates the profile log likelihood values when you given the other parameters. And here, let's say there are two covariates, gamma 1 and gamma 2, coefficient, gamma 1 and gamma 2. And the yellow circle indicates the true coefficient of gamma, which is 1.1. And the green axis indicates the profile likelihood estimates. And the red triangles is the estimate value from each model. So here, the left figure indicates the Bayesian model, which is the one-stage model. And here, the right figure is our models. And you can see our model can truly capture the true coefficient very well. So you can see that one stage of the Bayesian and the parameters of weight, like the weight parameters corresponding to that covariate is kind of like biased. So that's why we have to use two-stage approach to get the right coefficient of covariate. So here, we applied our model to 3 different types of data sets, but I brought 2 real data application. And first of all is the malaria incident case. So it's the malaria incidence in the African Great Lakes region. And there is about like 4,700 cases of malaria, and which is the count data set. And there are 3 covariates. The first one is average annual rainfall. The second one is vegetation index of the region. And the third one is proximity to water. So for the input data set X, we use the spatial basis function matrix with 239 knots. So we want to address the spatial patterns among the African Great Lakes region. So that's why we construct the basis function matrix using the template basis so that we can obtain these input data set. And we compare our model with Bayesian, which is the one-stage model. And also we compare our model performance with a spatial basis regression model. So this is the result. So you can see that our Bayes CGLM model shows the lowest RMSPE. And it shows the quite perfect, I think, yeah, 95% of coverage. And we can also quantify the uncertainty and estimation of coefficient compared to the Bayes CNN model. And yeah. Then the next really important question is how our uncertainty estimation and prediction contribute to the real world. I mean, yeah, how it is really important in science thing. So since our model can quantify the uncertainty and prediction, we can provide this insight that, so there actually over in the middle of the here, there's a lake. So when you're a policymaker or you have to make decision about the malaria incident thing, you have to think carefully about that prediction thing when you see that map. So when the point or the location is far from the lake, there will be more high probability of getting the prediction error. So you have to make carefully about that decision when you make that thing on that location. So that's the thing that our model can contribute to the science thing. Yeah. And the second application is brain tumor. So it's a brain tumor MRI image data set. And why is a binary data set, whether that 4,500 patients have a brain tumor or not. And we have two covariates from the image. It's the first order feature of the image, and the second order feature of the image is those are the covariates that we use in this model. And for the input data image, you can see over bottom of my slide, there's a four, you can see there are gray images. It's about the MRI image data set when you scan the brain. So also we compare a model with Bayesian and Rochester regression model. So note that even though Rochester regression model is really popular and general thing to apply the binary response data set, here we cannot just plug the input X image into a model. So here, the Rochester regression model, we only use the two covariates. And let's see how it works. So you can see in the GLM, which is a Rochester regression model, since we didn't combine the image data set into a model, it shows the lowest prediction accuracy on the accuracy and recall and precision. And compared to them, our model shows the really well accuracy, recall, precision model. And also our model provide the uncertainty estimation so that we can make that we can understand what kind of covariates are significant enough to state that those covariates are related to the response Y. So yeah, that's the benefit of our models. And then the next question is, then how the uncertainty in prediction contributes to the real world. So you can see the top panel illustrates the correctly specified images with small prediction errors. And the bottom panel illustrates the misclassified images with a large prediction errors. So when you're a doctor, you see that and you saw that, oh, there's a large prediction error, then you will go again to scan the MR data set, or you want to combine or try another approach to get the more data sets, something like that. So that's the point that I want to introduce. And yeah, these are the takeaways things that I want to point out. So our model is the unified framework to handle the two different types of data sets. One is the high dimensional variables, such as images or tensors or matrix. And the other one is the standard vector type variables. So in our model, we use the spatial basis function matrix, MRI images, and fMRI correlation matrix. And since we combine this image data set with a vector type covariate all together, so that we can show that our prediction accuracy improved, and also we provide the interpretation of the association between covariate and response. Second, also our model can quantify the uncertainty using the MC dropout by constructing the posterior distribution of the coefficient and predictive distribution. And happily, this work is published in January 2024 in Biometrics. And you can see the other mathematical thing that I put my effort along my PhD. You can see that on supplementary materials, and it's always welcome to discuss regarding these topics or any other based on deep learning or spatial modeling. And thank you for your attention. And yeah, thank you. Any questions? Am I too speak too fast?
Since your approach is like a two-stage approach.
Right.
You first use the base convolution neural network to get
Mhm.
the feed.
Yeah.
I'm wondering, like, is the quality of the feed will influence your final inference results? Like, for example, if I use other neural network or other things to get the feed and
Oh, so you mean not using the Bayesian deep learning model, or you
Yeah.
can extract the
or even
PCA?
some other things.
Yeah. That's a really good question. And we can do like we can do a PCA and or other dimension reduction method to obtain the fee, right? But since we want to, that's a high dimensional data set, and we want to take a benefit of using the convolutional neural network, which is well known for extract the information of the things, of the input data X. So also we want to adopt the MC dropout thing. So that's the reason why we chose the Bayesian deep learning model as one of the dimension reduction methods to use. Yeah. Mhm.
Following that question.
Uh-huh.
So, I'm curious, how sensitive the uncertainty quantification is
Mhm.
with respect to the tuning of your neural network? For example, if you change the dropout weight, if you change the width and the depth of the neural network, then is your algorithm sensitive to that?
So you mean about the hyperparameters of thing?
Yeah.
Yeah, so actually in our supplementary material, we have tested like how the dropout rate affects and how the length of the neural network affects. We have validated the thing, but it's robust, kind of robust things to obtain the posterior distribution. So it's stable. Yeah, right.
Stable.
Yeah. Mhm. Thank you for asking. Mhm.
Thanks for the
Oh, yeah.
So for the convolutional neural networks, do we design your own, or do you kind of use ones that are like off the shelf?
Can you come
That
again?
are like readily available like TensorFlow?
Oh, so how I model this, how I make that our model in what kind of tools?
Yeah, so there's like a bunch of already available.
Oh,
convolutional
yes.
networks,
Mhm,
and
mhm.
Or we
Oh.
like design our own.
Yeah, I use a Python, the tensor package. You can see there's also my GitHub. You can see my code over there. And yeah.
Thanks everyone, thanks for attending, and
You.
see you next week. I think it's